In this presentation, we will be talking about our own ring buffer lock-free executor for ROS2, which is based on Klepsydra's main product, the SDK. My name is Guillermo, and I'm part of the R&D team here at Klepsydra. Klepsydra is based in lock-free programming. This kind of programming is the high-level wrapper of the atomic operations in the processor, in particular the so-called compare and swap or CAS operation. It was invented back in the 70s, but it didn't really become popular until the early 90s, when it was implemented in higher level languages, and then it really took off when Java included it in the early 2010s. Lock-free programming consists on attempting repeatedly to write data in a small piece of memory until the data is in a consistent state. This is usually depicted as a plane trying to land in a busy airport. If the runway is busy, it flies away, and then it tries once again until it succeeds. This technique is substantially lighter than the traditional mutex operations because it is just specific to one small piece of memory, as opposed to a mutex, which blocks a big portion of memory. That is why the traditional lock systems are not deterministics, while lock-free systems are more granular and deterministic. It works remarkably more efficiently. The Klepsydra SDK lies between the operating system and the application. It is designed to simplify the implementation of code that collects and acts on data from multiple sources, such as sensor, external communications, and other events. Its goal is to perform operations faster and more reliably than using traditional locking mechanisms. Our own ring buffer is wrapped in what we call the Klepsydra SDK. It is just another library that's installed in the operating system that receives data from multiple sources. It is essentially a memory sharing system. Our ring buffer is enabled for two different approaches to data processing. The first one is the sensor multiplexer, which uses the ring buffer to process the same data multiple times simultaneously. One producer of data, usually large volumes like a camera or a lidar, and multiple consumers. The second one is the event loop, which uses the ring buffer to process, in a single consumer, data coming simultaneously from multiple sources. Producers can publish to the event loop at different rates, completely independent of each other. The ring buffer streamlines all this data and delivers it into a single-threaded consumer. The data flow process has very low latency. These two approaches have two main advantages. First one, very low power consumption, and the second one is a large throughput of processed data. Execution management in functionality is similar to that of ROS2 static single-threaded executors, where all subscriptions are run on the same thread. Implementation, however, is different. Klepsydra uses subscriptions as listeners, and timers are scheduled functions, all of which run on the same thread. Since the timers and subscriptions are single-threaded, there's no need to clone or to lock. Looking into the issues in ROS2, two of them can finally be solved by Klepsydra ROS2 Executor. The first one, the high CPU usage of the default ROS2 Executor. When large volumes of data or high-frequency data is being placed into the ROS2 Executor, the CPU consumption grows very fast. The second is that the ROS2 executor becomes unstable when large point cloud data is connected to many subscribers. One producer of this kind of data with many subscribers will drop messages without discrimination, with the risk of losing data. Testing scenarios were built for the above-mentioned issues and then validated in a Raspberry Pi 4. 3 executors were examined under these testing scenarios: the static single-threaded, the multi-threaded executor, and Klepsydra's own executor. Throughout these slides, green will represent ROS2 single-threaded executor, red will be ROS2 multi-threaded executor, and blue will be Klepsydra's own executor. In the first scenario, the results prove that Klepsydra executor needs substantially less CPU with moderate data rates, no matter the configuration. Importantly, as the number of publishers increases and the data rate gets faster, the difference in CPU consumption becomes considerably large. At a certain point, as you can see on the lower right graph, we can see that only Klepsydra processes all the incoming messages, whereas the other two executors cannot keep up and start losing critical data. As for the second test case, with the introduction of multiple subscribers per publisher, the obtained results were even better. The Klepsydra log-free executor can process substantially more volumes of data, where the other executors stop processing data. Klepsydra continues until the physical limit of the computer, utilizing all available resources in an optimal manner. We provide a factory of executors, which return shared pointers for interfacing. We need to provide some information. The size of the ring buffer. This is because we use static allocation in order to avoid allocating calls during runtime. This can be customized to tune the performance of the application. The factory can either be mapped to an event loop, a data multiplexer, or a series of event loops. We also provide a test version in order to simplify the debugging of the application. This third version runs in a synchronous, single-threaded blocking queue. We are currently improving the multiplexer executor. The goal is to provide a reliable executor for a single large producer of data. It is worth noting that if there are multiple producers of large quantities of data, then multiple multiplexer executors should be used. We have found in our performance testing that we are able to process large quantities of data and reduce power consumption. A possible topology would look like this: a flow of executors connected, sharing data and executing different tasks within it. The first node, a multiplexer executor, would be in charge of collecting data from the camera, both for further processing and for video streaming. The second node collects the camera information and adds the information coming in from the lidar and radar, and all of it is fed to a vision navigation system. Lastly, on the last connected node, the data is further enriched by the navigation sensors, which are fed to the application control loop. To conclude, when should you use Klepsydra's executor? Well, when dealing with large amounts of data, large number of sensors, and large number of publication events running with limited power, limited tolerance to data loss, and want to implement a solution quickly.
Hello, everyone. I'm here to present the second part of our video, which is focusing giving more details or explaining in more details how our streaming executor works. So the structure of the presentation is quite straightforward. First, a context, what is ROS2, what is the state of the art in terms of executors of ROS2. Then we will present our novel approach, our streaming executor, the performance benchmark that we used in order to verify the results, and then finally conclusions and future work. So what is ROS2? ROS2 is the second version of the robot operating system, which is an open source framework and a set of libraries that was mainly aimed as facilitating robotic application development, especially in multi-core environment. Moreover, recently there has been the development of the so-called Space ROS, which is a variation of ROS2 oriented to space applications, radiation-hardened computers, etc. Well, ROS initially was built in order to shorten and simplify the development effort related to robotic applications. And ROS2 also kept this goal in mind. There has also been some work in the area of real-time robotics. This was one of the main missing features of ROS1 that was introduced in ROS2. However, while this was one of the top priorities of ROS2, the performance itself, or the processing performance, was not. And therefore, it's not uncommon to find several issues in the area of latency, depending on the application and the type of computer, but also a strong excessive use of computing power and data losses. So these are some of the issues faced by ROS2 that we try to address with our novel approach. So how does ROS2 works? What is the ROS2 stack? In ROS2, the main concept is the so-called executor. which is the part of the application in charge of consuming the messages that come from the middleware. Usually, in the case of ROS2, it's a DDS middleware. So it's in charge of dispatching those messages to the application. However, the interface from the middleware to ROS is not the executor, but something else called the ROS middleware interface, or RMW for short. The RMW is what is really interfacing with the middleware, especially with the DDS. So it's a layer of abstraction of this that connects the middleware to the ROS client support library, which is one of the main core elements of the ROS2 library. Going further a little bit into what the executor is, like I mentioned, the executor is not directly connected to the middleware, but is actually connected to the RMW in order to receive and send messages to the middleware. So this is a very important element of ROS2, because as fast as you can get the executor doesn't mean that the system will be fast. There is a strong dependency on the application performance related to the RMW, but this is out of the scope of this research. What is the state of the art of ROS2? Besides the initial development of ROS2, there has been a lot of development in the area of executors in order to accelerate and fix some of the issues that I mentioned at the beginning related to latency and excessive computing power consumption. And there are three main executors currently in ROS2 that are most popularly used. Firstly, the single-threaded executor, which is a very simple executor that essentially takes the data from the RMW and send it to the nodes and subscribers without any interim steps. There is a static single-threaded executor, which is a variation of the previous one, but with the difference that there is only one in the whole system. That's why the name static comes from. And a very important feature that is also shared with the streaming executor, that we will see in a minute, is that the wiring in terms of which nodes, subscription, etc., are connected, it all happens during the construction of the executor and before the spin execution. The spin is the main method that the executor uses to start delivering messages. So during the execution of the spin, nothing of this happens, only happens before. This is a very important element, and we will come back to that later. Finally, there is the multi-threaded executor, which is a simple variation of the single-thread execution in which there are several threads delivering the messages to the different subscribers and nodes in the system. Now, the streaming executor, which is our main novelty, is based on what is called the Klepsydra event loop that was presented earlier in this video by Guillermo. And the concept that we follow in order to develop our executor is that the event loop will act as the actual delivery system, messaging delivery mechanism. So when we receive message from the RMW, they won't be sent directly to the nodes or the subscribers. They will be stuffed into the event loop, which will then be in charge of releasing these messages to the different subscribers. This is quite important, and we use the concept of public subscriber here, which is not the same as the publisher subscriber in ROS, because this is connected to the middleware. In this case, it's connected exclusively to the event loop. The streaming executor is very similar to a static single-threaded in the sense that everything happens, all the configuration happens at the construction level. And one of the things that happens is that nodes are mapped to event loops. This is a very important point. So if you have more than one event loop in the system, every node will be connected to just one event loop, not more than one. What is the implication of this is that every node is completely single-threaded. Every node runs, all the subscribers within one node are executed in the same thread. This is a key element in the whole definition of this system. So overall, nodes and event loops are mapped one-to-one. So we have two variations of the executor, the single-threaded, which is a simple variation that is depicted here. Every subscriber in ROS2, every node with its subscribers are mapped to a publish subscribe topic in the event loop associated to the node. So if two nodes, for example, are receiving data from the same subscribers, event loop will have two pairs, one for node 1 and one for node 2. This is very important because, like I mentioned before, every node is connected to one individual event loop. And this has some implications as well in the performance. So basically, the working system is quite simple. When there is a node subscribing to a topic in the event loop, we will create a topic, an internal event loop topic that connects the node and the topic name into a publish subscribe within the event loop. So there will be as many of those as nodes connected to the same subscriber. Obviously, different topics will also have different subscribers as well. So this is in a nutshell how it works. So when there is a new message coming from the RMW, for example, for topic 1, node 1 and node 2 are connected to topic 1. They will both have their own subscriber connected to the event loop. So we'll receive the data sequentially as whatever way the event loop receives the data. And the event will be published twice. Doesn't mean that the memory will copy twice. There will be just one memory copy, but the event will be published twice. The multi-core variations of the streaming executor is a simple extension. In this case, there will be more than one event loop in the system. Again, very important, nodes are associated to one event loop. So one node cannot receive data from two event loops. It will always receive data from one specific event loop. Why it put more than one event loop is in order to accelerate dispatching of messages, in order to accelerate the overall performance of the system, because you may have several nodes, some of them running completely independent, that can run on their own thread. So the event loop is able to distribute the load, receive the message from the RMW, and start releasing to the different nodes very efficiently. So when there are messages coming for the RMW, the streaming executor will determine to which event loops they should go, depending on the topic and the node name, and it will start publishing to each of them, which in turn will start sending the data to the corresponding nodes in the system. So in a manner, it works similarly to the static single-threaded, which performs a similar thing, but with just one thread. The event loops, the streaming executor does it with multiple threads, depending on the number of event loops configured in the system. So one key configuration element in the whole setup is the number of event loops that we decided to use for the executor. So when is interesting to use this system? When is interesting to use the streaming executor? The main reason to use this is when there is a large load of data in the system with limited processing power. When this is the case, definitely the event loop makes sense. When there is very low data in the system or arriving with very low frequency, there is the overhead introduced by the streaming executor make it unworthy of using it in this setup. There is a drawback in using the streaming executor is how to distribute the cores and the nodes, how to map which nodes should go to which cores. This is a very important element, and it's not trivial because some nodes may have a substantial volume of load and maybe the most processor intensive, while other nodes are more lightweight and less processor intensive. Some nodes may receive data at very high frequencies from different sensors, while others may receive maybe large volumes of data, but with very low frequency at the same time. So how to distribute nodes into event loops, this is one of the key elements. And for that, we have developed a new tool, which is a genetic algorithm that will perform some dry runs connected to the target computer running on board, but the genetic algorithm can run in a separate laptop or any other PC, and will provide the optimal configuration in order to reduce latency or increase throughput, depending on the customer needs, or also reduce CPU even if it's really of interest to the system. So how do we test this? How do we validate that our system works efficiently? We use the so-called real-time working group reference system, which is a tool used to verify the performance of the different executors, the different executions that are available. The setup, as you can see here, is quite a standard. It's exactly what the AutoWare reference system is built for. And when we optimize this, we use our genetic algorithm, in this case, we use it to minimize the average latency of the critical path, which is what the reference system is aimed for. So there is a critical path in the whole reference system, which, like you saw before, tries to emulate what a self-driving car system looks like. And there is always a critical path to be optimized. So this is one of the, as you can see here, and the paper gives you more details of where the critical path lies within this reference system. When we run our performance results, as you can see here, the performance of Klepsydra is consistent to what we mentioned before. For very small workload, as for example, in the case the first row in the table, number 64, this is the number of operations to be performed by the reference system. This is a very low number, and you can see that Klepsydra, yes, has a low latency compared to other ones, but it's worse than the single-threaded. Why? Because the overhead of Klepsydra makes the latency a little bit higher. However, as we start to increase the complexity of the calculations carried out by the reference systems, we can start to see that Klepsydra performs better and better than the other executors. And this is exactly what we were expecting. So for low volumes of data, Klepsydra streaming executors performs a little bit worse. For high volumes of data or high complexity system, it works substantially better. So in summary, what we're presenting here is a novel approach to ROS2 execution, combining a log-free ring buffer and the use of genetic algorithms to the optimization of the distributional load in the different nodes of ROS2. We have seen that this combination has proven to be very efficient, with a significant improving performance with respect to other executors in ROS2, and yet becomes very general. It can be applied to different configurations easily. In terms of the future work we're planning to do, the main area is to support more features within ROS2. At the moment, we don't support timers, and this is one of the first things that we are going to enable in the ROS2 plugin. Soon, there will be a release of the ROS2 Community Edition, in this case, supporting a single core streaming executor. We have another API, as was shown in the first part of the presentation, called the sensor multiplexer, that we want to introduce here as well, because it may increase the performance on certain specific variations of ROS2 applications, especially with LiDAR or cameras involved. And finally, throughout this year, there will be some testing on the RISC-V architecture. Thank you very much, and I hope you enjoyed the presentation. Bye.